Okay, so our next speaker is Nuette Heyns. Her title of her paper was called Word Embeddings for Recognized Multilingual Speech. Nuette, are you there?
Yes, thank you, Rainer.
Okay.
Um, I have shared my screen. Can you see it?
Yes, I can see it.
Okay. Okay.
I think you can begin.
Okay. So South Africa is a multilingual society where people often switch between languages in their speech. Now, code switch text corpora are hard to find as written materials tend to avoid code switching. And then the indigenous South African languages are also low resource languages. And adding to these resource constraints, embeddings are also usually trained using monolingual datasets that does not represent the syntactic structures and cross-lingual semantic associations of code switch data. Therefore, embeddings trained for South African languages require custom training techniques. So we propose to train word embeddings on a South African code switching dataset that consists of speech-to-text transcriptions of radio and television broadcast recordings. So several research have compared different word embedding architectures, and in most cases, it is found that when hyperparameter settings are standardized across different architectures, they all perform very similar. Thus, the specific embedding architecture is not of major importance as long as the hyperparameters are optimized for the specific task of interest. Now, the word-to-vec model is standardized with default values optimized for analogy tasks. So in this study, our main contribution is to show how the hyperparameters of the word-to-vec model should be chosen so that the models can be applied in the context of recognized multilingual speech, specifically in a South African setting. We will be evaluating embeddings resulting from different hyperparameter modifications to identify which hyperparameters should be adjusted and in what way. So to evaluate embeddings, there are two approaches using intrinsic and extrinsic tasks. Intrinsic tasks, for example, similarity and analogy tasks, are widely used to test the quality of word embeddings, but they do not always correlate to real-world applications. And extrinsic tasks um, evaluate how well embedding performs on a real-world application. So some studies investigated the relationship between the intrinsic and extrinsic evaluation methods and all concluded that there is no direct correlation between the performance of an embedding on an intrinsic task and their performance on a real-world problem. So we propose to extrinsically test our models by applying it to text classification. And because we are working with television and radio broadcasts, it is natural to classify the data into 5 categories, namely news, advertising, sport, traffic, and weather. So when creating a word embedding model, there are a few default parameter values that should be fine-tuned to fit the evaluation task as well as the data set. So we'll quickly look at the main characteristics of some of these parameters. So the embedding size is the number of dimensions in the embedding layer. And in theory, if the embedding dimension is higher than the vocabulary size, it will lead to overfitting because there is no crossword interference and the embedding would resemble a one-hot encoding more than a true embedding. Therefore, the embedding size should correlate to the dataset size. However, one study suggests this might rather be task specific. So, for example, text classification uses fewer dimensions than sentence generation. Then the window size is the number of context words around a target word. So when using a smaller window size, the clusters will show interchangeable terms. So synonyms and antonyms are clustered together. And with a larger window size, the clusters are expected to show the relatedness of words, which is preferable with tasks like text classification. And then the training time is the number of times the algorithm iterates over the training data. So of course, increasing the training time can be computationally expensive, especially with larger data sets. So that's just something to keep in mind. And then the model ignores words that occur less than a minimum count. And for a large data set, this parameter is less important. Then one study found that a higher learning rate over a longer time is beneficial for rare words, but that a learning rate decay ultimately creates better word embeddings. And to optimize the word-to-vec model, negative sampling is used. So with negative sampling, the calculations of the loss function are only performed on a subset of the input and thus speeds up the process. And then lastly, the exponent of negative sampling is used to shape the negative sampling distribution. So if alpha is 1, words will be sampled in proportion to their frequencies. If alpha is 0, all words will be sampled equally, and a negative alpha value will sample low frequency words more than high frequency words. So for our data, we use speech recognition outputs produced by a commercial speech recognition system developed by Cygen on South African radio and television broadcasts obtained from a company called Novus. And then the data set includes recordings of 103 different South African radio and television stations. And on these stations, 12 different languages are spoken. We used only the English radio station data, so this included a lot of code switching to the other languages, and is a useful representation of spoken South African English. And this graph shows the amount of data in each language if only the English radio stations were used. And after pre-processing, the data set consisted of 100K words, which were split into a training and a test split of 70K and 30K respectively. Then to compare the level of code switching in the dataset, we use the M-index and the I-index. So the M-index quantifies the ratio of languages in the corpus based on the Gini coefficient. It measures the degree in which a language is distributed in the dataset, but it does not indicate if the languages are integrated with each other, and therefore it's not proficient for indicating whether code switching occurred or not. So the I-index is used to complement the M-index by summing up the probability that there has been a switch. A valuable benefit of the I-index is that it does not require dividing the dataset into utterances or for it to contain competing weights. So to measure the M-index and the I-index, each word in the corpus has to be tagged with the languages. So for this we used Watlang, which is an extension of FastText's language identifier model that can identify languages on a word level. And we trained custom models for the South African languages and used them to identify each word in the corpus and tag them with the language identifier. So the distribution of the languages in the dataset was calculated using the M-index that scored 0.32, and this indicates an uneven representation of the different languages. And then the number of times a language switch occurred in the data was calculated using the I-index that scored 0.29, which suggests a large amount of code switching. Then we used a continuous bag of words model to train our word-to-vec models using code switch datasets. So for a baseline model, we implement a simple bag of words model for which the parameters have been optimized. And we use the code switch dataset for this as well. And then we also will be comparing our word-to-vec model with a pre-trained glove model. Now the range for each hyperparameter we explore in the study are listed in the table. The red values are the default values. And then a logistic regression classifier was used to evaluate the performance of the embedding on the text classification task. So the dataset was tagged with the appropriate categories. And the dataset mostly consisted of sports and news data, with the rest of the classes combined, forming just 25.5% of the data. And naturally, the embeddings are expected to perform better with the high resource classes. So we compare the feature selection models with precision recall curves. We also use microaveraging, which considers each element of the class indicator matrix as a binary prediction. And for the initial test, each hyperparameter was changed in isolation, so the effect that it has on a model, on the default model, can be observed. And then the model showed a 6% increase in performance when the embedding size was increased to 250. And after that, the model stopped showing further improvements. But the biggest improvement in the model's performance was seen when negative sampling was used. So a small sampling rate of 5 was enough to increase the model's performance to 25%. And then the experiments showed that changing the other hyperparameters in isolation has no effect on the model. So we continue to hyperparameter optimization by looking at the effect that some of the hyperparameters have on each other. And since there are too many combinations to exhaustively test all the interactions, we discussed 5 combinations that were found to interact significantly. So we found that changing the negative sampling in combination with other hyperparameters can have a significant effect on the model. However, when combined with the window size or minimum count, it has no effect. We also found that when changing the negative sampling rate to 5 and using a unigram distribution where alpha is 0, the performance increased with an additional 2%. This combination continued showing the best performance independent of how other hyperparameters were changed. Then the optimum time to train a model when negative sampling is optimized is 10 epochs, after which the model's performance starts to decrease. And then when combining the learning rate with negative sampling, a 10% improvement is made. And using the default smooth unigram distribution where alpha is 0.75, the model will benefit by a smaller learning rate, but ultimately the model will perform better when using a unigram distribution where alpha is 0 in combination with a higher learning rate of 0.025. Then when the window size is 30 or higher, all minimum count values achieve the same performance. And overall, changing the minimum count and window size do not show significant performance differences in the model. Although when these two parameters were changed in combination, a slight improvement of 1% was achieved that resulted in the best performing model of our task. Then for our task, we found that increasing the embedding size, the window size, the training time, and the negative sampling rate creates a better model. And negative sampling distribution should be decreased. And the model showed a 31% improvement in the default values when the values are optimized. Then lastly, we compared the default and the optimized word-to-vec model with a bag of words baseline model, as well as a pre-trained glove model. So the default model is outperformed by both the pre-trained glove model as well as the bag of words model, but the optimized code switch model shows competitive results. The performance of the pre-trained glove model demonstrates two important things. First, it is important to optimize the model's hyperparameters to suit the task, and secondly, the dataset should be appropriate for the application environment. So the fact that our relatively small code switch dataset performed better than a similar embedding pre-trained on a much larger monolingual dataset suggests that training embeddings on a code switch dataset when it will be used in a code switch environment is more important than the size of the dataset the embedding will be trained on. So to conclude, we found that fine-tuning the embedding size and adding negative sampling in combination with choosing the appropriate distribution for negative sampling to the model are very important. And other hyperparameters such as the window size, training time, and the minimum count do not make a difference when they are changed in isolation, although the combination of these hyperparameters is somewhat important. And then we found that optimizing the parameters can produce a 31% performance improvement on the task. And when comparing the code switch model to a bag of words baseline model and a pre-trained glove model, we found that the optimized word-to-vec model outperformed the pre-trained models and showed results that are competitive to the bag of words model. So these findings show both the importance of optimizing certain hyperparameters to fit the task and the potential of embedding representations to process recognized multilingual speech. Thank you.
Thank you very much.